Okay, so kind of getting into isotopes a little bit further, we're going to look at the isotopes of chlorine 35 and chlorine 37. So they're both chlorine, but they're going to have different masses, okay? They differ in only their mass. And this is because if I look at chlorine 35 and I look at chlorine 37, okay, they're still chlorine. So that means that their atomic number is still 17 because they're still both chlorine. So they still have 17 protons. So that's what makes them chlorine, are those 17 protons, but they differ in the number of neutrons, which is going to differ in their mass. Their nuclei are going to weigh more or less depending on how many neutrons are housed there. So I can look here and I could figure this out. So protons here are 17, and the neutrons, all I'm going to do is I'm going to subtract 35 from the 17 to get the number of neutrons. All right, so here we have, let's see, we got 20. Can't do math today. And here I have 18, right? Yeah, 18. Okay, so one has 2 more neutrons than the other, so this one, chlorine 37, is heavier. Now, if you look at your periodic table, I want you to look at the average atomic mass. That number is the decimal that is usually right below the chemical symbol. All right, so for chlorine, if you look, it shows that its average atomic mass is 35.453 AMU. So if I look at that number, all right, it's not exactly the average of 35 and 37. So average atomic mass, you think they would take the 2 isotopes and they would average them out. So I would add 35 plus 37, divide by 2, and that number should fall in between 35 and 37. But it doesn't. If you look, it's 35.453. That's not directly in the middle of the 35 and the 37. Why? Well, because in nature, isotopes don't exist in a 50-50 fashion. So it doesn't happen that way. The one that is the most stable is going to be found more often and in higher percentages. We call that percent abundance. Okay, so in order to calculate average atomic mass, what we do is we use the mass abundance or percent abundance to calculate the average atomic mass. So basically what happens is the average atomic mass is a weighted average, kind of like your grades are. Not all of your grades have the same effect on the overall percentage. Some have a higher effect, some have a lower effect. And that is what we use to calculate average atomic mass, is that weighted average. So chlorine 35 is more stable. It's the more stable isotope. Therefore, it is found 75.77% of the time when we're looking at chlorine atoms. So all of our chlorine atoms in the universe, 75.77% of them are chlorine 35. Chlorine 37 is not quite as stable, so it's only found about 24% of the time. And so what we're going to do is take a weighted average of the two to get to that 35.453 AMUs that we see on the periodic table. Now, one of the things is you can easily look at the periodic table and the numbers of the average atomic masses, and you can determine what is the more abundant isotope by looking at and just doing some brain math here. So if I look at that number, 35.453, okay, I can tell that, well, 35 must be counted more often because that number is closer in the average atomic mass, okay? Because if there were more of 37, you would expect the average atomic mass to be closer to that 37 number, but it's not. It's closer to the 35. So without even knowing what the most abundant isotope is, I could make a prediction just kind of based off of the number on the periodic table. I would say chlorine 35 is more abundant.